Hello everyone, welcome to this online course on material science, and I am Dr. Imtiaz Ahmed. In this lecture, I will try to give some basic definitions and notations that are used in the field of magnetism. The quantity that I want to discuss first is known as magnetic dipole moment. To understand what this quantity is, let's assume that we have a closed circular loop which is carrying an amount of current I. We can associate an area vector with this closed loop which is pointing outward from the loop, and we can denote this differential surface area by the quantity ds. Now, due to this flow of the current in the closed loop, the loop will produce magnetic flux which will come out from this side of the loop and will re-enter from the other side. So if you want to draw some magnetic flux line, this will be the direction. It is as though this loop has a north pole somewhere here where the flux is coming out, and the south pole here where the flux are coming in. That's why these current carrying loops are usually known as dipole. It has two poles, and one can define a magnetic dipole moment for this current carrying loop by the quantity d mu, which is the differential magnetic dipole moment, and is defined as quantity which is I, the current carrying by the loop, times the area vector. And depending on the problem, one can integrate out the area to find out the total magnetic dipole moment. And there are some other physical quantities of interest which are commonly encountered in magnetic study of magnetism. I am quite sure all of you know about these quantities, but I just want to mention about them here to make this lecture more complete. So we start from like magnetic flux density, magnetic field intensity, we have magnetization vector, we have magnetic susceptibility, then free space permittivity and free space permeability. And all of this quantity are denoted by these symbols. With these symbols in mind, we can estimate an energy of a magnetic dipole moment when placed in a magnetic field. So let us assume that the magnetic field is pointing in this direction and the magnetic dipole moment is pointing in this direction, which is denoted by the quantity mu. Now, the energy of this magnetic dipole moment in the presence of the magnetic field is defined by the quantity E and is equal to minus mu, the magnetic dipole moment, dotted with the externally applied magnetic field. Now, if you expand this dot product, you are going to get something like this. Minus mu is the magnitude of the dipole moment, so we need the magnitude, and we need the magnitude also of the magnetic field, and then cosine of the angle between these two. Now, when the magnetic moment is aligned with the magnetic field, in that case we have theta is equal to 0 degree. Then the energy is minus mu times b. But when the magnetic moment is anti-aligned, like pointing opposite to the magnetic field, then theta is 180 degree. So cos of 180 is minus 1. So in that case, we have energy of the dipole moment is mu plus mu b, right? So this minus sign is ensuring that when the moment aligns the magnetic field, we have a lower energy which is minus mu b, and when the moment is anti-aligned the magnetic field, the energy is maximum, which is plus mu b. So that's the convention of the minus sign here. Also, we need some basic relations between these physical quantities. For example, in the free space, B and H is related by this relation. And if there is a presence of a magnetic material which has a magnetization vector m, then this equation changes a bit, and we have to add the m with the magnetic field intensity vector. And if we assume that the field strength is not that high, then we can assume the assumption of the linearity, then the magnetization vector of the material is proportional to the magnetic field intensity vector, and the proportionality constant is what is known as the magnetic susceptibility. This quantity is quite interesting and quite important. It will come in our next lecture. So you can think of this as a ratio of this magnetization and to the magnetic field of the inside the solid. Before I end this lecture, I want to emphasize another important quantity, which is known as the Bohr magneton. To understand what this quantity is, we need to understand a simple model of a hydrogen atom. So what we have inside a hydrogen model, right? We have a proton in the center, and electrons are kind of revolving around the protons. It's just a model, right? We are assuming that electrons are circulating around a circular path with the radius r. Now, recall from your first year physics courses that the Bohr model of atomic physics says that only those paths are allowed around the proton. For the electron, only those paths are allowed where the quantity mvr, which is actually the angular momentum of the electron moving with the velocity v in the path r center away from the proton, should be integer multiple, where n is an integer number of the reduced Planck constant. And the reduced Planck constant is by definition is Planck constant divided by twice pi. So when n is equal to 1, then electron is in its ground state, right? The energy is in a state where the energy of the electron is minimum in the hydrogen atom. So for n is equal to 1, we can see that mvr, this angular momentum, turns out to be the reduced Planck constant. Okay. Again, we know when electrons moves in a closed circular path or a charged particle moves, there is a magnetic dipole moment. So we need to estimate what is the magnetic dipole moment if the electron are moving in its ground state. To estimate that, we note for the fact is that the current due to this electron moving in the circular path can be defined as the amount of charge the electron carrying, which is minus e, times the tau. Tau is the period of the revolution. And we need to understand what this tau is. So how much time it takes to make a complete revolution. It's the path, which is like twice pi r, the periphery of this circle, and also is divided by the velocity of the electron. Now, we know just from a couple of minutes ago that the magnetic moment of this electron is defined as the amount of current it's creating times the area of this loop, which is pi r square, right? Now we can manipulate this expression and try to understand what is the value of the magnetic moment. For example, let us replace the equation of I here, which is minus e times tau. So here we can write minus e tau, pi r square. And then if we replace tau by twice pi r by v, you can see we will have something like e by, we have vr by 2, right? And we can bring the electron mass here. So we write m here and m in the numerator. So, and this is according to the Bohr in the ground state of the electron, it should be h, right? Or sorry, the reduced Planck constant h bar. So if you replace mvr with h bar, then what we have is, let me write it here, we have e h bar by twice m. So this is the quantity of interest, because we know the mass of electron, we know what is the reduced Planck constant, and also E. So this quantity without the minus sign is known as Bohr magneton. So what it defines that the amount of magnetic dipole moment of an electron when it is orbiting inside the hydrogen atom in its ground state. That's what this Bohr magnetron is. And you will see in different literature, people use this unit of Bohr magnetism to quantify materials magnetization strength. So we will see these things in future. So if you want to have a read about all of the things that I have discussed today, have a look in this book, which is Magnetism in Condensed Matter by Stephen Blundell in the chapter 1. In the next lecture, I will start with different types of magnetism. I think that's about it, and thanks for listening.